One challenging thing we need to be able to do is name compounds if we're given the chemical formula. The challenging thing about this is there are 3 sets of rules depending on whether you have a covalent compound, an ionic compound, or an acid. Now, technically, acids are simply a type of covalent compound. However, I'm putting them in their own category here because they have their own set of naming rules. So whenever you're asked to name a compound, the very first thing you should do is decide, is it covalent, ionic, or an acid? And if we recall, covalent compounds are made of nonmetals only. Ionic is a metal plus a nonmetal or a polyatomic ion, or sometimes it can actually start with a polyatomic ion. The only time this is the case if it starts with NH4+, which is ammonium. But the key thing here, it has a metal or a polyatomic ion in it. Acid, its giveaway is it starts with a hydrogen. So HCl, things like that, where the very first element is hydrogen. So once you've established if it's covalent, ionic, or an acid, then you can move on to actually naming it. So let's look at the naming system one type at a time, and we'll start with covalent because they're the easiest. Once you've established you have a covalent compound, you're going to use this general format to name it. Essentially, you're just going to name both of your atoms that you have, but you're going to use prefixes to tell how many of that atom are in your compound. And the second element, you're going to erase its ending and replace it with IDE, Ide. So the prefixes are just the standard prefixes that we have to use for naming. So for instance, 1, if you have 1 of something, that would be mono. 2 would be di. 3 would be tri. 4 is tetra. 5 is penta. 6, hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is, deca. So we do have to memorize these, but a lot of them we should already know because we've seen them in other places. Decade, that's 10 years. Octagon, 8. Pentagon, 5. Triangle, 3. Things like that. So we just need to keep these in mind. The easiest ones to mix up are 6 and 7, so be careful of that. I like to remember 6 and hexa both have an X in them, so that's how I know that they're associated. But we're just going to use those prefixes to determine how many of each element we have in the compound. One little note, if you only have one of the first atom, for some reason we leave off the mono prefix, so it just doesn't get a prefix at all. Let's look at some examples. So our first example is PF5. So the first atom is phosphorus. We only have one of it, so because it's that first atom, we're not going to give it a prefix. So we're just going to write down its name, phosphorus. Second atom, we have 5 of it, so we use a prefix. The prefix for 5 is penta. And then we just name him, changing the ending to IDE. So instead of fluorine, I'm going to write fluoride. Phosphorus pentafluoride. Let's look at another example. N2Cl3. All right, we don't have one of the first guys, so we are going to use a prefix. The prefix for 2 is di. So I use the prefix and then just write the name, nitrogen. So dinitrogen. We have 3 of the second thing, so he gets the prefix tri. And his name is chlorine, so I'm going to change that to chloride. Dinitrogen trichloride. So naming covalent compounds is pretty straightforward as long as you know your prefixes. Now let's look at ionic compounds. These are usually pretty simple, but there's one thing about them that can be a little tricky sometimes. If we determine that we have an ionic compound, we're going to use one of these 2 general formulas here. And the only thing that's different is in the top one is when it's paired with a metal, and in the bottom one is when it's paired with a polyatomic ion. Generally, we're going to name the metal, and then we'll either name the nonmetal, but again, change its ending to IDE, or we'll name the polyatomic, and we just leave the name as is. So it should be ending in ate or ite, because almost all of our polyatomic polyatomic ions end in either ate or ite, so you just don't even worry about the name. One thing that's a little weird, notice this parentheses here. In this parentheses goes the charge on the metal for transition metals. The thing about ionic compounds is we don't use the prefixes to indicate how many of each element are in the compound because we can figure it out based on the charges. So in every case, we have to have a charge-neutral compound. So that means I always have to indicate the charge on the transition metal so I can figure out how my positive and negative ions pair up. For instance, let's say I had sodium, which makes a charge of +1, and chlorine, which makes a charge of -1. Since this is +1 and -1, to be charge neutral, I'm just going to need one of each, so it would just be NaCl. On the other hand, let's say I had barium, which has a +2 charge, and chlorine, which is a -1. For this to be charge neutral, if I have a +2, I need more than one chlorine. This is just a -1. So if I want my positive and negatives to be equal, I'm going to need a second chlorine so that overall there's a charge of -2 here and a charge of +2 here. So BaCl2. So with ionic compounds, we don't need prefixes to figure out how my elements are going to match up. We use the charges to do it instead. And that's why there's no prefixes in the formula. The tricky thing is for transition metals, they don't have a set charge that they always form. Their charge changes. So in order to figure out how these would match up, we have to figure out, okay, what is the charge on that thing? So for instance, let's say we had Fe2+, and he had to get together with oxygen, +2 and -2, so those two would get together directly, FeO. But Fe can also form a 3+. And oxygen here is still 2-, and we see right now they don't match. So I have +3 and -2. So I need more negative stuff, so I make another one over here. But now I have -4, and that's too much, so now I have to add another iron here. So now I have a +6. Okay, that's too much, so I add another -2. So now I have a total of -6 and +6. Those charges will cancel out, so I'll need 2 irons for every 3 oxygens. So we can see iron would pair up with oxygen differently depending on whether it's a 2+ charge or a 3+ charge. So we need to tell what the charge is on those transition metals so someone else can figure out, well, am I dealing with 2+ iron or am I dealing with 3+ iron? Again, it's only for transition metals because the main group metals in columns 1 and 2 always form the same charges, so we don't have to worry about those. So let's look at some examples of how we do this. Let's start with something that's not a transition metal. So in this case, we would start up here. Once we decide it's ionic, we're going to use this general format. Let's start with this example down here. MgNO2, 2. So we're just going to name the metal, Mg. So that's going to be magnesium. And we're going to name the second piece. We can see this isn't just a nonmetal, it's a polyatomic, so I'm just going to name him NO2, that is nitrite. And because magnesium is not a transition metal, I didn't have to worry about the parentheses there. So that's it, magnesium, nitrite, and I'm done. Okay, now let's try another one. Now let's try one with a transition metal. Fe3P2. So I would start out the same way. Okay, I've got an ionic compound, so first things first, I'll name my metal. So my metal is iron. Because it's a transition metal, I'm going to leave a parenthesis here that I'm going to go back and fill in later. And now I have just a nonmetal, so I'm just going to name him, turning my ending into IDE. So that was phosphorus, so he becomes phosphide. So metal, nonmetal. Now I need to fill in these parentheses. So in order to do that, I need to figure out, okay, what is the charge on iron so I can put that number in here. I always like to make a little, I call it a T-chart when I do this. So we have this. And I make a T-chart to separate the elements. I look and say, I have 3 irons. I don't know what its charge is. But I have 2 phosphorus, and from the periodic table, I can figure out that the charge on phosphorus is -3. So 2 times -3 means I have a total charge of -6 here. And in order for this whole thing to be charge neutral, that means I must have a +6 total from the ions. Well, if I have 3 of those ions and they add up to be +6, each one of them must be +2, because 3 times +2 gives me +6. Therefore, each ion must have a charge of +2, and that's what's going to go in the parentheses. But just for fun, we write it in Roman numerals. So this would be iron 2 phosphide. So the naming part, really, you can do without just right away, just name the metal and the nonmetal. And then to get this charge, we have to do a little bit of work. So I prefer the T-chart method. There are other ways to figure it out, but I think this is a really easy way to do it. So Fe3P2, we would call iron 2 phosphide. And notice that 2, again, is the charge on the metal. It's not how many it is, it's what the charge on it is. Okay, let's try another one. This one down here. And this one seems a little trickier, but it's really not. So notice this one has this funny added piece right here. This is called a hydrated compound because it has a bunch of waters attached to it. And all we do is we name our first half of the compound like normal, and then we're going to add on something that tells me we have 7 waters attached. And the way that you always do this is you add on a prefix to tell how many, and then the word hydrate, like hydration stands for water. So as soon as I see 7 waters, I can go ahead and write that part. Okay, at the very end, I'm going to have a prefix. Prefix for 7 is hepta. And it's a bunch of waters, so I'm going to say heptahydrate. So that waters just go down here. And then this part of the compound I can name like normal. I can totally ignore the waters now. I've taken care of them with the heptahydrate. So now let's go up here. We say, okay, Ni, I'm going to name my metal. That guy is nickel. Nickel is a transition metal, so I'm going to leave a parenthesis and go back and fill it in later. I only have to do that for transition metals. And now I see NO3, that is the nitrate ion. It's a polyatomic, so I don't change the ending, I just leave it in, or leave it as is. So I have nickel something nitrate, heptahydrate. And now I just need to figure out this piece. I'm going to do the same thing I did before. I have nickel, NO3, 2. I'm once again going to make my T-chart, but this time I'm going to leave the polyatomic as a big group, because I know the charge on nitrate. So I have 1 nickel, and I'm trying to figure out his number. I have 2 nitrates, and I've memorized that nitrate has a -1 charge. So overall, I have a -2 on this side. So I must have a +2 on the nickel side. So nickel must be +2. So nickel 2 nitrate, heptahydrate. So overall, ionic is pretty straightforward. We just use this metal, and then you either name the nonmetal or the polyatomic, so that part's pretty easy. If you have a transition metal, you have to do this extra step here, where you need to figure out the charge on the metal and put it in the parentheses here. If you have waters attached, really simple, that's called a hydrated compound, and you just add a little ending prefix hydrate. So the prefix is the number, and then hydrate stands for the fact that it's waters. So this long thing right here would have been nickel 2 nitrate heptahydrate. Okay, that's molecular compounds and acids. Now let's look at, that's molecular compounds and ionic compounds. Now let's look at our acids. I'm getting ahead of myself. Oops, not what I wanted. So acids we identify because they start with a hydrogen. That's pretty easy. And there are 2 types of acids that we can have. The first type is a binary acid. So that has a hydrogen, and then it has some non-metal atom, so just a single type of atom attached to it. The other type is called an oxyacid, whereas it has a hydrogen, and then that's attached to a polyatomic ion. And they have different systems depending on which one you have. So a binary acid is super easy. You just use this general formula, hydroblankic acid. So you just fill in this blank with basically the name of whatever the nonmetal is. Oxyacids are also pretty simple. They take one extra step. You're going to name the polyatomic ion and then write the word acid. And then you're going to change the ending of the polyatomic ion. So if it ended in 8, you're going to erase that and turn it into ic, right here. If it ended in ite, you're going to erase that and turn it into ous, us. So I say the little phrase to myself, 8 goes to ic and ite goes to us, and it helps me remember it. 8 goes to ic, ite goes to us. So first thing first, after you figured out it's an acid, ask yourself, well, is it a binary or an oxyacid? And then pick which set of rules you need to learn or use. So look at some examples down here. The first one we have is H2S. So it's an acid because it starts with an H. And then it's just a hydrogen and one other type of element, sulfur. So that means it's a binary acid. So I'm going to follow this general formula. So H2S would be hydro. Always starts hydro. And then S, sulfur. Fill in the blank and end it with ic. And then I write the word acid. So H2S is hydrosulfuric acid. All right. On the other hand, let's say we have H2SO3. So it's an acid because it has a hydrogen in front. But I can see it's not attached to a single element. It's attached to a polyatomic. That makes it an oxyacid. So all I'm going to do, I'm going to start out by writing the polyatomic's name and the word acid. So SO3, that is sulfite, and then the word acid. And then I think about how I'm going to change that. So sulfite acid, I'm going to cross out ITE and replace it with OUS. Now, because it's sulfur, we also sort of make it sulfurous acid. So this is going to be sulfurous acid. So that's just a weird naming thing for sulfurs, that sometimes that UR disappears and sometimes that UR comes back. So it's a little odd. But now we have sulfurous acid. So all I did was write out the polyatomic and then scratched out the N and wrote in the new ending. On the other hand, we have H2SO4. So again, starts with an H. That's why I know it's an acid. But it's paired with a polyatomic, so it must be an oxyacid. So I'm just going to write out the polyatomic name and then the word acid. SO4, that's sulfate. And then I'll write the word acid. And I say, okay, I'm going to use this system. I'm going to cross out the 8 and turn it into ic. So I will rewrite this sulfuric acid. So this is why we have to have different rules for each of these, because H2S is hydrosulfuric acid, H2SO3 is sulfurous acid, and H2SO4 is sulfuric acid. So we had to find a naming system that gave us different names for each of these three compounds, and that's why we have the set of rules we have over here. So overall, we need to be able to name covalent compounds. We use prefixes. Ionic compounds, it's metal plus a nonmetal or metal plus a polyatomic. Sometimes we have to give the charge of a transition metal. Or acids, which start with an H, and we have to break them up into these two categories, binary acids and oxyacids.